Hi, everyone. So today we're going to go over mortality rates. So the first thing to note here is T of X is a representation of the future lifetime of a person aged X. So if a person is aged 35, T of X represents the future lifetime or the number of years, continuous random variable that the individual currently aged X will survive. And so Sx of T represents the probability that aged X individual survives at greater than T years. And so the way to get that, if we only have the survival function at age zero, is survival function at age zero at x plus t over survival function at age zero at x. So you're saying what's the probability that a person who is aged zero will live greater than x plus t years, given that he has already lived x years? That is how you get Sx of t, which is the same notation wise as xpt, where x represents the current age of the individual and t represents the number of years that the individual will live, or the probability that the individual aged x will live t years, more than t years strictly. And so this is another notation for 1 minus the survival function, or the probability that an individual aged X will die within the next 2 years. This notation is a representation of an individual aged X will survive U years, but then will die the following T years. So this can be broken down into the probability that an individual aged X survives the next T years, and then an individual aged X plus mu dies within the next T years. Or actually, this is supposed to be mu. This is supposed to be mu, right? This is supposed to be mu. So an individual aged X survives mu years times the probability that an individual aged X plus mu dies within the next T years. Now, the discrete version of this, as we noted, the continuous version of this is T of X, and this is continuous because you can die at any day, any moment. But the discrete version of this is the floor of the continuous random variable T of X, and this is the number of completed years that an individual aged X has completed. If we're looking for the probability density function for X for an individual aged X, and the variable here is T, where T represents the number of years, continuous variable that aged X has left to live, that can be represented as the probability that aged X lives at least T years times the probability that aged X plus T dies within the next moment. So this represents the force of mortality at age X plus T. The discrete version of this, so the probability that Kx, so the discrete version, so the number of completed years, again, discrete equals K equals the probability that aged X survives at least K years times the probability that X plus K dies within the next year, because they have completed exactly K years. So they have lived at least K years. So it could be anything past K, but to ensure that we don't go beyond the year, so we don't go beyond 2 or 3, we want to make sure to multiply by the probability that X plus K dies within that next year. So that's when we do the product of those, that's when we get to the probability Kx equals K. Now, this equation is a very fundamental and very important probability that the number of completed years is greater than K is equal to the number of completed years is greater than or equal to K plus 1. And now, because we know that this survival function, the probability that aged X survives at least K plus 1 years is strictly greater than, right? Then we have to have an X plus 1 here. So that's a key thing to note. And then here are the 3 different ways or forms that we can represent the age X living to mu years and then dying within the next T. Adjusted force of mortality. So if we have a force of mortality, we'll want to adjust it by either multiplying it by a constant K or adding to a constant K. We can see how that translates over to the MPX versions, where we add a constant, raise it to the power of that constant, or we multiply by e to the negative that constant times n. And then here we can also see TPX written in the form of an integral where we have the probability that x will survive s years times the probability that x plus s will die immediately within the next moment, sum across all of those probabilities from t to infinity. That's the probability that x will survive at least t years. So once again, the probability that x will survive at least t years is the probability that x will survive at any point between t and infinity, but then will die within the next moment. The summation, the sum product of all those possibilities is this integral representation. Similar thing for the probability that aged x will die within the next t years is we take the probability that x will survive s years times the probability that x plus s will immediately die at that moment. And this is the sum product from all 0 to t. And then similar logic for the other deferred case. Next, we talked about how t of x, tx represents the future lifetime, continuous lifetime of an individual aged x. Talked about the expected value of t of x. It is also the integral of the survival function as well. So that is another way that you can actually get to the expected lifetime of individual aged x is by taking the integral of the survival function. And then we have similar concepts and notations for the discrete version, how to find the expected value for the discrete version. Next, this is where the concept of deductibles also kick in, where we know the concept of a deductible when we're doing integration is from 0 to the level of the deductible is what the client pays, and then after a certain point, that's the limit and where the insurer starts the payment. And so we can think of the deductible as sort of this cutoff that we have. So from 0 to n, right, we have the random variable t of x, but then we're going to put a cap on the age to n. So if the future lifetime is greater than n years, we're going to just say it's n, right? We're not going to keep the value of the actual lifetime. We're going to cap it at n. And so again, this is very similar to the deductible integral. And we can take this as integral from 0 to n of the survival function of tpx. Again, this is very similar to the survival function formula for the deductible. If you recall, that was 0 to n of the survival function of x dx, where we have this sum deductible d, right, from 0 to, let's say, sum deductible d, right? This is the client portion. But then after we get to d to infinity, that just stays at d. So that's representation of the client payment. That simplifies down to the integral of the survival function. That is the exact same concept and idea here. And the notation for that is over here. Again, very common and important that you know the notation for this. It's called the n-year temporary complete expectation of life. We have constant. Now, these are the four main subsections that are important to this mortality rate section is constant force of mortality for all ages, constant number of deaths each period, constant force of mortality between integer ages, and then constant number or uniform distribution of deaths between integral ages. So the first two, constant force of mortality between ages or for all ages, and constant number of deaths each period is referring to the ages. So from age 1 to age 2, force of mortality is going to be the same from age 2 to 3, 3 to 4, and so on. Right? It is independent of the age. Same for the uniform distribution of deaths. The number of deaths from age x to x plus 1 is going to be the same as the number of deaths from age x plus 2 to x plus 3, and so on. So we have this uniform distribution of deaths. The number of people that die between the ages are same for all of the ages. And so we can represent this as a uniform distribution from 0 to w minus x, where w is the representation of the max number of years that the individual can live. And so we start off with kW, right? The way that this goes is we start with kW, and then each year, k people die, exactly k. That's what we refer to as the uniform distribution of deaths across the ages. So we're able to represent this as a linear function. And then we're able to plug in the TPX as the ratio between the number of survivors at x plus t over the number of survivors at age x, able to take the ratio of that, and we deduce it down to this representation. We're able to take the integral of that, and we're able to get what's the expected value, temporary and n-year temporary complete expected value. So that is from the integral from 0 to n, and this is the formula that we get when we do that integral. And this is very intuitive, because if we think about, okay, if we're going to cap this at n, and we know that there's a uniform distribution of deaths, what is the expected lifetime? So for example, if it's x and we're going to cap it at 2, meaning that, right, it has to be less than 2, right? This is just nature, has to be less than 2. Meaning that if the actual lifetime is greater than 2, we're just going to leave it at 2. We're just going to leave it at 2. It's going to be capped at 2. Now this represents the probability that x lives at least n years, so lives at least 2 years, right? Times that value, so times 2, right? So that's our value, right? If it's greater than 2, what's the probability that it's going to be greater than 2, which is npx, plus n over 2, and n over 2 is because it's uniform between integer ages, right? It's uniform between integer ages. So that's why it's n over 2. We're going to take n over 2, so in this case it will be 1. It will be 1. And then times the probability that age x will die within 1 year, or within 2 years. And so that's our probabilities. So it's a very intuitive formula once you actually dive into it. Now, as we mentioned, we have deaths between integer ages. And again, you want to use a linear interpolation for this. So this is the entire idea that, hey, if you want to find the number of survivors at age, let's say 20.3, that is going to be the weighted average of the number of deaths, of the number of survivors, right? Number of survivors at age 20 and the number of survivors at age 21, where the weights will be the proportion of time that has passed. So 0.3 weight will go to actually 21 because it's further from 21, and then 0.7 will go to the 20 because it's closer to 20. So that's what we can do when we have uniform distribution of deaths between integer ages. And then we have finally have forceful mortality is constant between integer ages, and we have the similar notation here. So again, 4 main subsections: forceful mortality, uniform distribution of deaths across all ages, forceful mortality being constant, uniform distribution of deaths across each individual age. And so that's where we can use this to fractional ages as well. So that was a high level idea and concept of mortality rates that I wanted to cover.